The theory is used to explain the structure of molecules, covalent molecules, with the help of the repulsions between the different types of electron pairs present in the valence shell of central atom. In the central atom of the covalent molecule, there may be lone pairs of electrons and there will be bond pairs of electrons also. There is a repulsion between the electron pairs because electrons are having negative charge. The like charges will repel away. So there is natural repulsion between electron pairs. The repulsion between the lone pairs of electrons is the maximum. Then comes the repulsion between lone pair and bond pair. And the least repulsion between bond pair and bond pair. So based on that, we can give the structures of the covalent molecules. We are talking about the structure of water molecule. Let us see again, water molecule. You know, the electron dot representation of water molecule, H2O, the electron dot representation is like this, H, O, H. And on the oxygen atom, there will be two lone pairs, non-bonding electron pairs. This is the structure of water molecule based on the electron dot representation. So in water molecule, we have two different types of electron pairs. One is a lone pair. There are two lone pairs of electrons. Two lone pairs of electrons. And oxygen-hydrogen covalent bonds. There are two covalent bonds between oxygen and hydrogen. So there are two bond pairs also. Bond pairs also. Let us see the distribution of these electron pairs. The electron pairs can be distributed in such a way that there is minimum repulsion. There is minimum repulsion between them. The repulsion between minimum repulsion between the electron pairs. Then only the structure will be having stability. So pair of electrons. The repulsion between the electron pairs should be the minimum so that the structure is having the highest stability. So to have maximum stability, there should be minimum repulsion between the electrons. And how are these electron pairs, 4 pairs of electrons, are arranged around oxygen atom to have minimum repulsion? And the modern views say that the distribution will be like this. You consider a structure of a tetrahedron. Structure of a tetrahedron. And what is a tetrahedron? Structure of a tetrahedron like this. This is a tetrahedron. Tetrahedron. Tetra means 4. Hedra means side. So there are 4 sides. A three-dimensional figure with 4 sides. Let us say what the sides are in the given structure. Say you mark this as A, B, C, D. The structure can be marked like it's a 3-dimensional figure. All these A, B, C, D, all these 4 atoms are not lying on the same plane, but it is a 3-dimensional figure. And Consider the triangle ABC, ABC, that is the rear side, the back side. Consider ABC, 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 it is this side, the left side. You consider ACD, that is the right side. Then you consider ABD, that is the back side, the rear side. And you consider BCD, that is the base of the figure. So there are four triangular sides. Four triangular sides are joined together. And such a structure is called a tetrahedron. At the center of the tetrahedron, there will be the oxygen atom. The oxygen atom is at the center of the tetrahedron. And the 4 electron pairs, see here we have 4 electron pairs. And these 4 electron pairs will be directing towards the corners of the tetrahedron. So, one pair of electrons, say, will be here at this corner. So, the structure is like this, one pair of electrons. Second pair, say it is here. It is here. So, the structure will be like this. Then third electron pair, say here. So, the structure goes like this. And the fourth electron pair here, and here there is the structure. See, so this is the distribution of the 4 electron pairs. Remember, on the oxygen atom in water molecule, there are 4 pairs of electrons, 2 lone pairs, see here, lone pairs of electrons, and 2 bond pairs of electrons. There is repulsion, and the repulsion should be the minimum, so that the structure is maximum stable. And maximum stability can be attained if these electron pairs, 4 electron pairs, are directed towards the coordinates of a tetrahedron. So at these coordinates, there will be the electron pairs like this. Now, out of these 4 electron pairs, 2 electron pairs are bond pairs. 2 are bond pairs. Suppose we have the hydrogen atoms here. There is hydrogen atom 1. So this electron pair is corresponding to hydrogen. Here there is oxygen. And here there is another hydrogen atom. And these are the lone pairs of electrons. These are the lone pairs of electrons, and the other 2 are bond pairs of electrons. Now you take the structure outside the tetrahedron. You take the structure outside the tetrahedron. Then the structure will be like this. Say there is oxygen here. There is a hydrogen atom here. Then second hydrogen atom here. And electron pair, 1 electron pair. See here. Here there is electron pair. And here also there is another electron pair. That is structure. Electrons are not having, say, considerable size. So you neglect the size of the electrons. You consider only the atoms, hydrogen and oxygen atoms, you consider. So the shape will be V shape. Now it is here inverted V shape. So it is a bent molecule. If it is the structure, what should be the bond angle? The bond angle, this one. Or you take this one, the bond angle. This is not the bond angle, here there is no bonding. This is the bond angle. So, this is not a bonding, here there is no bonding. Okay, you take the bond angle between these 2 oxygen hydrogen bonds. The bond angle is expected to be, if this is the structure, the bond angle is expected to be 109 degrees 28 minutes. That is the expected bond angle. But the actual bond angle in water molecule, H, say OH, the actual bond angle, that is 104.5 degrees. 104.5 degrees. And why the bond angle is reduced? That is because there is strong repulsion between the lone pairs of electrons. With the lone pairs of electrons, there is strong repulsion. And so the lone pairs are coming closer to the bond pairs of electrons. And so the bond pairs will be coming closer like this. And the bond angle reduces to 104.5 degrees. 104.5 degrees. If you make use of the electron dot representation, say like this, the bond angle should be 180 degrees. As I mentioned in the last class, if we consider only the p orbitals, bonding with the p orbitals, then the bond angle should be 90 degrees, 90. But the actual bond angle is 104.5 degrees in water molecule. And that is due to the strong, the lone pair repulsion. There is a lone pair repulsion. Due to the strong lone pair repulsion, the lone pairs of electrons are coming closer to, they are coming closer to the bond pairs of electrons. Here we have the bond pair, see here. And so what happens? The bond pair will be coming closer and the bond angle is reduced to 104.5 degrees. Thus, we can explain the structure of a water molecule with the help of the valence shell electron pair repulsion theory. Here we have considered the electron pairs in the valence shell of the central atom, oxygen atom. Similarly, we can give the structure of ammonia molecule, NH3 molecule. Do you remember the electron dot representation of ammonia molecule? The electron dot representation of ammonia molecule is like this. This is the structure of ammonia molecule. There is a lone pair of electrons on the nitrogen atom. And there will be 3 bond pairs. Say one lone pair of electrons. And here 1, 2, and 3. 3 bond pairs of electrons in ammonia molecule. Totally we have 4 pairs of electrons. 4 pairs of electrons. Out of these 4 pairs, one is lone pair, non-bonding electron pair, and 3 are bond pairs of electrons. So the structure should be as before. The nitrogen atom is at the center of the tetrahedron, and the electron pairs will be directed towards the coordinates of a tetrahedron. And so, say the structure will be like this. There is nitrogen atom, and here there is a lone pair of electrons. Here there is a bond pair of electrons, bond pair. Here another bond pair of electrons, and here a third bond pair of electrons. Now you join these ends. Say these ends are joined. Then what you get? You will get the structure of a pyramid. There is a structure of a pyramid. There is a trigonal pyramid. Because you are neglecting the size of the lone pair. You neglect the size of the lone pair. Neglecting the size of the lone pair, you consider only the atoms. So if you consider only the atoms, say 3 hydrogen atoms and 1 nitrogen atom, then the shape is a trigonal pyramidal structure. So nitrogen atom is at the apex, at the top of the pyramid, and at the corners of the base, there will be the hydrogen atoms. And at the top of the nitrogen atom, there will be a lone pair of electrons. Now, there is a repulsion. If this is the case, the expected bond angle is, as before, it is 109 degrees 28 minutes. But the actual bond angle is, in this case, it is 107 degrees only, slightly less than the expected 109 degrees 28 minutes. That is because there is a repulsion between the lone pair of electrons, lone pair and bond pair of electrons. There is a repulsion. And due to that, the lone pairs of electrons will be coming closer. And so the bond angle will be reduced to 107 degrees from 109 degrees 28 minutes. Thus, we can give the geometry of ammonia molecule. So, in general, based on the electron pair repulsion theory, we can give the geometry, the shape of covalent molecules by considering the repulsion between lone pair, lone pair, lone pair, bond pair, bond pair, bond pair. Lone pair, L-O-N-E, L-O-N-E. Then lone pair, bond pair, L-O-N-E, then B-O-N-D. And finally, bond pair and bond pair, B-O-N-D, B-O-N-D. The repulsion will be the maximum in the case of the repulsion between lone pair and lone pair, L-O-N-E, L-O-N-E. Then comes L-O-N-E, B-O-N-D. And the least repulsion between two bond pairs of electron, bond, B-O-N-D, B-O-N-D. That is the least repulsion. So based on that, we can explain the structure. You consider only the electron pairs in the valence shell, outermost shell of the central atom. We can explain the geometry from the repulsions. Okay. So that's about the VSEP-RT, valence shell electron pair repulsion theory. Can you follow this? You may be having some confusion regarding the tetrahedron. Don't you have it?
Yes, sir.
Yes, say the fact.
Yes, sir.
Is it clear or not? Tetrahedron?
With H2O and NH3.
Not clear. Okay, yes. Don't worry about. Yes, you should have some doubt. You should have some doubt. And you have to ask me. Some doubt will be there, and I shall explain that in the next session. In the next session, the tetrahedron will be coming again. We have a topic known as hybridization. Hybridization. So in the hybridization, the tetrahedron will be coming again. So when I explain hybridization, I will bring the tetrahedral model. Can you see this pen? Tell me.
Yes.
Yes, sir.
Open your mouth. Can you see this?
Sir.
Yes, sir.
So I shall make the model, physical model I shall make. And I shall show you when I explain hybridization. Then the tetrahedral model will be very clear to you. Okay? So you please show some patience till I explain the hybridization. There will be a slight doubt regarding that. Okay, we will make it clear when we explain hybridization. Okay, so all right. Okay. Now let us go to the potential energy curve of a hydrogen molecule. The potential energy curve of a hydrogen molecule. Potential energy curve. Potential energy. Potential energy curve of hydrogen molecule, H2 molecule. How H2 molecule is formed. We have seen how hydrogen molecule is formed. When hydrogen molecule is formed, two hydrogen atoms are coming closer. Two hydrogen atoms are coming closer. And the electron pair will be shared between the hydrogen atoms, so that both the hydrogen atoms will be getting the duplet structure, duplet electronic configuration, doublet electronic configuration of the nearest noble gas, helium. That is what we have already studied. Let us see the condition of two hydrogen molecules coming closer. Say we have two hydrogen molecules, hydrogen atoms. So here there is hydrogen atom. That is the nucleus of the hydrogen atom. That is having positive charge. Am I right? Nucleus hydrogen atom. It is having +1 charge. There is one proton. So it is having positive charge. And around this, there is a one electron. There is a one electron. There is attraction between the nucleus and the electron. Okay. Let us take the second hydrogen atom. Similar is the case of the second hydrogen atom. You call this a hydrogen 1. Hydrogen 1. Second hydrogen atom, the nucleus positively charged, and here there is a the valence electron, one electron, and that is the second hydrogen atom. Let me call it as H2, like this. Second hydrogen, hydrogen 1, hydrogen 2. That is the structure of the two atoms. When these two atoms are coming closer to form H2 molecule by sharing of a electron pair, what happens to the potential energy of the system? When the hydrogen atoms are coming closer, two types of forces are experiencing there. One is the attractive force. The other is the repulsive force. There will be attractive force and the repulsive force. Two types of forces are acting here. One is attractive force. Then second one is the repulsive force. Two types of forces. Repulsive force. Let us see what are the two types of forces. Attractive force, that is between the nucleus of a hydrogen atom 1 and electron of a hydrogen atom 1. Do you agree with that? There is attraction between nucleus of a hydrogen atom 1 and electron of a hydrogen atom 1. Okay. So one attractive force is there. That is between the nucleus of one hydrogen atom and electron of the same hydrogen atom. So attraction between nucleus of one hydrogen atom and its own electron. That is one attractive force. There is a attraction between hydrogen atom number 1 and the nucleus of a hydrogen atom number 1. Nucleus of one hydrogen atom. First hydrogen atom, one hydrogen atom, and its own electron. That is one type of attractive force. Second, see the two atoms are coming closer. Then attraction between nucleus of one hydrogen atom and electron of another hydrogen atom. That is also possible. The first one is attraction between nucleus of one hydrogen atom and its own electron. For example, attraction between nucleus of H1 and its electron. Similarly, attraction between nucleus of a second hydrogen and its own electron. That is very natural. Second attractive force, that is between nucleus of one hydrogen atom, and electron of another hydrogen atom. There is also a chance for the attraction because nucleus is positive, electron is negative. So there is natural attraction. So the second type of attraction is the attraction between nucleus of one hydrogen and electron of another hydrogen. For example, nucleus of a hydrogen 1 and electron of a hydrogen 2. Then nucleus of a hydrogen 2 and electron of a hydrogen 1. These are the two types of attractive forces. When the hydrogen atoms are coming closer to form the H2 molecule, hydrogen molecule. Now you think of the repulsive force. Here also we can see two repulsive forces. One is the repulsion between nuclei of two hydrogen atoms. Two hydrogen atoms are coming closer. They are approaching each other. The hydrogen atoms are approaching each other. So there will be repulsion between positively charged nucleus of the two hydrogen atoms. So repulsion between nuclei of two hydrogen atoms. Two hydrogen atoms. That is one repulsion. Repulsion between nucleus of H1 and the nucleus of H2. Okay, that is one repulsive force. Second one is the repulsion between electrons of two hydrogen atoms, between electrons. Electrons are negatively charged. So electrons of two hydrogen atoms. Two hydrogen atoms. So here also we have two repulsive forces. One is repulsion between nuclei of two hydrogen atoms. Second, repulsion between electrons of two hydrogen atoms. So there are two types of forces here, attractive force and the repulsive force. Attractive force will bring the atoms closer. Attractive force will bring the atoms closer, while the repulsive force will keep the atoms away. Is it not? The attractive force will be bringing the atoms closer, while the repulsive force will keep the atoms away. And there should be an equilibrium position at which the attractive force balances the repulsive force. The attractive force balances the repulsive force. And at that condition, there is formation of the covalent bond between the two hydrogen atoms. So if we draw the potential energy curve, see, it is like this. Here you can plot potential energy, and here there is a internuclear distance. The internuclear distance between the two nuclei. So at the beginning, the two atoms are far away. There is no interaction between the atoms. Before the formation of the H2 molecule, the atoms are far away. There is no interaction. There is neither attraction nor repulsion. Such atoms are coming closer. So they are coming closer. So at the beginning, the potential energy of the system is found to be, say, zero, somewhat zero. There is neither attraction nor repulsion. But when the atoms are coming closer, that means the internuclear distance decreases. The internuclear distance decreases. Then slowly the energy of the system decreases, and there is a minimum energy condition. And at that position, the bond is formed between the hydrogen atoms. At that position, the repulsive force and the attractive force will be counterbalanced, will be equal. And there is formation of the hydrogen molecule, H2 molecule. Suppose the atoms are coming still closer, then what happens? If the atoms are coming still closer, then the energy of the system increases, and it increases like this. See? So this is the condition at which the hydrogen molecule, at this condition, hydrogen molecule is formed. At this level, hydrogen molecule is formed. And here, the energy, if you measure, it is found to be, do you remember the bond enthalpy of a hydrogen? It is 435.8 kilojoules. That will be the energy of the system. And you measure the internuclear distance. Distance between the nuclei of the two atoms. Do you remember the distance between two nuclei? That is called, what is it? It is called the bond length. That is called the covalent bond length. And it is found to be 74 picometer. 74 picometer. And this is the bond length. The bond length or bond distance. So at this distance, if the distance between the two nuclei, hydrogen nuclei, is 74 picometer, that is the balancing position. At that position, the system has the minimum energy and maximum stability. Minimum energy, maximum stability. And there is the formation of H2 molecule at this condition. The nuclei cannot come more closer than 74 picometer. If the nuclei are coming closer than 74 picometer, then there is a repulsive force again. Naveen?
So, like, why is it like from the right side, right to left?
See, internuclear distance increases from, say, left to right. The arrow mark is there. You look at the arrow mark.
Like you explained, like.
See, atoms are here. They are far distant. Here there is the nucleus, one atom. Here there is a second atom. Okay, second atom. So this is the internuclear distance now. Okay, far away, far away, far away. Now what happens? These atoms are coming closer and closer. See? So closer and closer. So this distance decreases. This distance decreases. Follow this or not?
Yes, sir.
Okay. So the distance is decreased. So this is decreased. The internuclear distance is decreased. And here there is a sudden dip. A dip in the energy. Okay. And it reaches a minimum. And this is the minimum equilibrium position between here there is the formation of the hydrogen. There is formation of the hydrogen molecule. See, here the distance. This is the internuclear distance at this condition. And that is the position at which the hydrogen molecule is formed. This is the condition at which the covalent bond is formed between the hydrogen atoms. That is the equilibrium distance. Okay. And that is the bond length or a bond distance. The bond distance is nothing but the internuclear distance in the bonded case. In the bonded molecule, the distance between the nuclei, that is the bond length. Okay. Suppose these are still coming closer. They cannot come closer because then the repulsive force between the nuclei and the electrons increases. So there is a sudden jump in the energy of the system. When energy increases, what happens to stability? Decreases. You take our own case. If we are healthy enough, if we have sufficient energy, then we will not simply remain on our bed. Do we? We will come outside, we will wander here and there, we will play. Okay, you are very active. If you are in the high energetic condition, you are highly active. You are mobile. You are not simply lying and sleeping on your bed. But you are not taking food enough. Your health condition, that is worsened. The energy condition, that is lowered. Then what happens? Can you go out of the room?
No.
Suppose one is sick, eh? Severely sick, not even say water is taken, then what happens? There is no sufficient energy, bedridden, we say. Less energy, more stable on the bed, more stable on the bed. That's all. And finally, suppose death occurs. Death occurs. The biochemical changes do not take place in our body. So there is no creation of energy in our body. So what happens? The energy is the least and the stability is the maximum. We cannot move. We are lying still, and four of the people will be coming and carrying us to the graveyard. Not we are moving, we are moved by the others. Got the idea? Got it?
Yes, sir.
So minimum the energy, maximum the stability. So this is the minimum equilibrium position, and that is the most stable condition. So that is the potential energy diagram, potential energy curve of a hydrogen molecule. So 74 picometer, that is the equilibrium intermolecular distance or the bond length of a hydrogen atom. Okay, sorry, hydrogen molecule. Hydrogen molecule. If they are coming, they try to, suppose they try to come closer, they cannot, because the energy of the system will increase and the system will become unstable. All right. So you must ask the questions. You should not try to hide away from me, as Navin did. You just come forward. If you got any doubt, you ask me. If I can, I shall explain. If I can, I shall explain. If I cannot, I will frankly say, no, I cannot. I will refer and explain. Okay? Don't believe that I know everything under the sun and above the earth. No, I'm not a man like that. I'm a man of a little knowledge, very little knowledge. Okay? So that's about the potential energy diagram of a hydrogen molecule. All right? Do you follow this or not?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
that is no problem. Now let us go to two theories. One is valence bond theory. It's a new topic. Valence bond theory, VBT. Valence bond theory, VBT, valence bond theory. That is giving us an idea regarding the formation of a covalent bond. All the time we were talking about the covalent bond and ionic bond. And more emphasis is given to the covalent bond formation. That is to explain the geometry, the shape of the molecules. Okay. We have drawn the electron dot representation. That is one approach according to Lewis. According to Lewis, that is one approach. Then there is the valence shell electron wire repulsion theory. That is another approach. Another research paper. Research work done by a group of scientists. They are giving the theory like that. All are different approaches. Okay. Then now we try to explain the formation of a covalent bond in the view of valence bond theory, VBT, valence bond theory. It's a very simple thing. Not a simple thing. For us, we can minimize it. We can study it in a simple way. According to this theory, a covalent bond is formed by the overlapping of half-filled atomic orbitals. Say, covalent bond is formed. This is talking about the covalent bond formation. So, covalent bond is formed by overlapping. So far, we had not talked about the overlapping of the orbitals. I shall say what is meant by overlapping. So, covalent bond is formed by is formed by overlapping half-filled, half-filled, half-filled atomic orbitals. No, atomic orbitals, half-filled atomic, half-filled atomic orbitals. There is overlapping of a half-filled atomic orbitals. Then pairing of leading to pairing of electrons, leading to pairing of electrons, pairing of electrons, and sharing of electron pairs, sharing of electron pairs, electron pairs. The last portion we have already seen what in a covalent bond there is electron pairing and sharing of electron pairs. And how does the electron pairing occur? To occur, the electron pairing half-filled means one electron. The maximum capacity of an orbital is equal to 2 electrons, is it not? Maximum capacity of orbital is equal to 2 electrons. If there is only one electron, then it is a half-filled orbital. Half-filled orbital, not orbit, not a subshell. I say orbital. So here comes orbital. With that view, we have already studied about orbitals. S orbital, P orbital, D orbital, like that. We have studied. Now, here the clear picture of the covalent bond formation is coming according to valence bond theory. Electron pairing is there. Sharing of electron pairs, it is there. And for all this, first of all, there should be overlapping of atomic orbitals. Overlapping of atomic orbitals. What is meant by that overlapping? Overlapping means merging together, interfering together, merging together. Say, here there is one s orbital, and here there is another atom with a s orbital, not the circle. This is not the circle. This is a sphere. So the s orbitals, these are coming closer. Here there is one electron. Here also there is one electron, suppose. Then when these two are coming closer, ultimately what happens? As in the case of hydrogen atom, these s orbitals will be, say, merging together like this. The s orbitals will be merging. Say, this is the common space for both the orbitals. There is merging. Do you follow what I say? And this merging of orbitals, that is called overlapping. So the new idea is only overlapping of atomic orbitals. The rest is the same. We have already studied in the previous classes. During the formation of a covalent bond, there is electron pairing. One electron each, electron pairing. There is sharing of electron pair. All these things are there. At the same time, a new idea is introduced here, and that is about the overlapping of the atomic orbitals. The overlapping atomic orbitals should be having one electron each. There should be one electron each. See, here there is one electron, and here there is one electron. So, after overlapping of, after merging of the half-filled orbitals, there is electron pairing and sharing of the electron pair. The new idea is only the overlapping or merging of atomic orbitals. Okay. So the s orbit will be overlapping like this. This is a common space. There is a common space for both the orbitals. Okay. That is called overlapping. That is over. Okay. So the different types of overlapping, we can see the next. It is time now. Let me stop now. All of you are there or not? Hello, friends. You are there.
Yes,
So
sir.
according to the valence bond theory, VBT, Vidur, what is the new idea introduced?
Overlapping.
Overlapping of atomic orbitals containing one electron each. Half-filled atomic orbitals. After that, the electrons will be getting paired. And the pair of electrons will be shared by the combining atoms. So only overlapping is the new idea. Atul, Krishnan, Sharon, Malavika, Michael, Mikhail, Naurin, Nivya, Alvin. Follow this or not? Next day we
Yes,
can
sir.
see the various types of overlapping. Say you are changing the type of or the study of chemistry. Eh? You are advancing, going ahead. Slight deviations from what you studied in the lower classes. Am I right? You are going
Yes.
up. There is a building up. So let us see the overlapping next day. Then there is a hybridization. Then finally we have molecular orbital theory. All these things will be included in the coming examination. Half-yearly examination. You know, basic concepts. Then structure of atom, periodic classification, and this chapter also. That is a chemical bonding. All these
Sir.
chapters will be there for the coming examination.
Sir.
The model I will give.
Excuse me, sir.
Ah,
Sir, after hybridization, can you explain again the VSC PRT,
what else?
like of ammonia and H2O?
In hybridization, all these molecules will be coming. Don't worry. Ammonia, water molecule, all these will be coming in the hybridization. That is why I just jumped. Don't worry about that. Okay, let us meet again.
Thank you, sir.
Thank you. Let me stop now.